So we are going to find a matrix in a linear transformation that corresponds to reflecting a point across the line y equals mx. So for example, if we have some point over here and we reflect it across this line, it's going to end up somewhere over here on the opposite side of the line. Now, the y equals mx case is very difficult to deal with. So let's see if we can get some information by looking at a simpler case first. Let's look at the idea of reflecting across the y-axis. So say we have some point xy over here, and if we reflect it across the y-axis, it's going to end up on this side, and the only difference is going to be that the x component becomes negative, right? When we reflect across the y-axis, the y-coordinate is going to stay exactly the same, and we're just going to flip the x-coordinate. But the idea of x and y coordinates is not particularly helpful when we're looking at a general case of a line. So let's look at this a little deeper. First of all, instead of thinking about x and y components, we want to think about the parallel and perpendicular components of some vector. So if we think about this point, instead of having x and y components, but as having parallel and perpendicular components, then it becomes a lot easier to deal with. What we see is, because we're looking at the y-axis, the y-coordinate is going to be parallel to the y-axis, so it's parallel to the line, and the x-coordinate is going to be perpendicular to our line. So what this transformation corresponds to is we're keeping the exact same parallel component, because we still have the same y value, but we're taking the perpendicular component and making it negative. Now let's see if we can generalize this to our case with y equals mx. Instead of looking at the point xy, let's look at, we have a perpendicular component here, and then we have a parallel component going this direction. And then we add these two vectors together to get to our original point. And we'll call this point here, since it's a vector, we'll call it v being xy, with a different xy than over here. But what we want to look at is making the perpendicular component negative. And if we do that, if we figure out a formula for doing that, then that corresponds to reflecting the point across y equals mx. So now what we have to do is figure out these parallel and perpendicular components. So in order to find the component of v that's parallel to the line, we'll call the line L and use something called the vector projection of v onto L, which says that if we imagine having our vector v here and our line L going this direction, the vector projection just says what happens if we only take the component that's parallel. It's sort of like if we had a sun up here and we're casting a shadow onto L, what shadow does the vector v make? And that is going to be the component of v that is parallel to our line L. The problem with this formula is that when we look at the formula for vector projection, we're going to get v dot L over the magnitude of L squared times L. All of these L's are treating L as a vector. So we need to have some formula for our line that's composed of a vector rather than some formula like y equals mx. In order to do that, we can just look at the fact that one of the vectors on our line is 1m. And the reason for that is that the slope of our line is m. So every time we go over 1 in the x direction, we go up m in the y direction. So we can substitute L being equal to 1m everywhere in this formula and then figure out what that gives us. Now, v is going to be xy. So we can substitute all of that in. We're going to get xy dotted with 1m over, and then we want the magnitude of L squared. Well, the magnitude of L is going to be the square root of 1 plus m squared by the Pythagorean theorem. So then we square this. Our denominator here is going to be 1 plus m squared. And then we're multiplying this by 1m. Now we can do this dot product that's happening on the top here. First we have 1 times x, which is just x, and then we have m times y over 1 plus m squared times 1m. So this is the vector projection of v onto the line L, or equivalently onto the vector 1m. Now this is helpful, but it's not all that we want, because we do know the parallel component now, but we also need to know the perpendicular component in order to do this reflection. To do that, let's look at this triangle. We have the vector v going out here, and we have the parallel component. And notice if we add the parallel component with the perpendicular component, that's going to get us to our final point. So if we take the vector projection, which is the parallel component, and add the perpendicular component, we get to the vector v. So if we want the perpendicular component, we just subtract the vector projection. And then that gives us that the perpendicular component is going to be v minus the projection. And of course, this is the projection of v onto L. So we have our perpendicular component here. Let's figure out what our final reflection formula is going to look like. First, we know that we're adding the parallel component. So we're going to take the projection, and then instead of adding the perpendicular component, we're going the other direction. So we're going to subtract the perpendicular component. And this is going to be our final answer, t of v. Now we want to figure out what this is. We know that the perpendicular component is v minus the projection. So we have the projection minus v minus the projection. And then we have a minus minus becomes a plus. So we have 2 times the projection and then minus v. And now we can plug in all of this information over here and get to our final solution. So I've erased the board a little bit to give us some space, and it's time to just do this final computation. So first, we're going to take 2 times the projection, and we know the projection is equal to this over here. So we have 2 times x plus my over 1 plus m squared times 1m. And then we subtract v, and we know v is just xy. Now we have to bring all this stuff together. So let's take a look at the first vector. First, we have 2x plus 2my over 1 plus m squared. That's going to be our x component. And then we do the same thing on the bottom, except it's going to be times m. So you have 2mx plus 2m squared y over 1 plus m squared. And now if we want to add these 2 vectors together, we're going to write these in terms of a common denominator. So we'll multiply the top and bottom here by 1 plus m squared. So we're going to get 1 plus m squared x over 1 plus m squared, and then 1 plus m squared y over 1 plus m squared. Now we want to bring these together. So let's start out by looking at the x's on the top here. We have 2x minus 1x, so that's going to be a 1x, and then we have minus m squared x. And then we're going to divide by 1 plus m squared here. And then on the top, the only y is going to be this 2m over 1 plus m squared y. Now we want to look at this bottom section here. When we look at the x's, again, all we have is this 2mx. So you have 2m over 1 plus m squared x. And then for the y's, we're going to get 2m squared minus m squared. So again, we're going to have this m squared y. And then we also have a minus 1y. So m squared minus 1 over 1 plus m squared y. And this is the formula for the linear transformation of xy. And if we want to write this as a matrix, then all we would have to do is take out these pluses and these x's and y's just like this. So right here, this is our matrix A, corresponding to the linear transformation of reflecting some point xy across the line y equals mx using our projections.